Everyone, we're still together here so far. The same types of problems. Okay. Oh, okay. I'll continue. Thanks for allowing me to continue. Right. The next problem we're going to look at is also. Wait. Yeah. Ask. Mr. P. Yeah. May you go back to the previous slide. This one here. Yeah. Okay. Negative term minus to negative term 10 sine over minus sine minus cos and minus tan. Did I see it right? Yeah, therefore. Yes. These, they are multiplying each other here, ne? So I'll just put a different color for brackets to show that they are multiplying each other there. So that it doesn't look like we are saying that they subtract each other. You see, it's multiplication there. So just be aware of that. So the negative divide by the negative gives you positive, but then we're only left with one negative sign. Hence, our answer is a negative 10 because, yeah, at the bottom or at the top, it doesn't matter. We are left with one negative sign, which is multiplied with a positive sign and gives us negative. Is there anything else that's not clear on this problem here? No, it was very clear. Everything is clear. All right. So on the same page, still we're looking at a grade 11 problem from our Siavula learning guide. And it's page 259. Ne? I'm just noting these so that should you want to do your self-study with the same learning guides which are on Classroom, you don't struggle. So we're going to do one that looks like this. Cos squared of 360 degrees plus theta, and we add it to the cos of 180 degrees plus theta multiplied by the tan of 360 degrees minus theta multiplied by the sine of 360 degrees plus theta. On this problem, I won't be drawing the cast diagram because at this point we need to learn how to think about which quadrants are at play without having to make a reference drawing. Ne? So I'm just upping the ante a little so that we challenge our minds a bit and we depend on our memory. So 360 degrees plus, it's first quadrant. When we reduce that angle, this is just cos squared of theta. 180 degrees plus is third quadrant. Cos is negative. So I'll just make a square bracket. So this becomes negative cos theta multiplied by 360 degrees minus theta is fourth quadrant. So tan is negative. So we'll say times negative tan theta. And 360 degrees plus theta is first quadrant. So that reduces to sine theta. And this we can just drop down. Cos squared theta plus the negatives multiply each other out to give you positive. We can write tan theta as sine theta over cos theta because it's a quotient identity. And when we do that, we will have cos theta times sine theta over cos theta times sine theta. This gives us cos squared theta plus these two divide each other out to give us 1. So we're only left with sine theta multiplied by sine theta, and that gives us sine squared theta. And guess what? This is 1, which is a square identity. So again, these are the types of problems that go for like 3, 4, maybe 5 marks, depending on the grade. So in matric, maybe roughly 5 marks. But I'm just doing them because they're a good way to jog our memory when coming to simplifying stuff. Now, I want us to look at a couple of numeric problems of a similar pattern. So still on the same page. In the same learning guide, page 259. This is for your self-study. I'm just noting that. We will look at the problem that says the cos of 300 degrees multiplied by the tan of 150 degrees divided by, that shouldn't look like a 6, so that is not 360. The sine of 225 degrees times the cos of negative 45 degrees. Right, so at the top, what do you think we can do with the angles? I'm thinking 300 degrees can be written as 360 degrees minus 60 degrees. And 150 degrees can be written as 180 degrees minus 30 degrees. And this is a interesting way to think about it, because the fact that it gives us 30 degrees and 60 degrees means that we can use special triangle that has a 60 degree angle, a 30 degree angle, and a 90 degree angle. And at the bottom, since we have a 45 degree angle, maybe we could also use the 45 degree angle triangle. And we can also reduce 225 to 180 degrees plus 45 degrees. Can you see how that can help? So when we think about the 225 degrees as 180 plus 45, then it takes us to a specific quadrant, but it also makes us be able to work with a special triangle that has 45 degrees. Just as 150 degrees can be written in with regard to 30 degrees, and 300 degrees with regard to 60 degrees. So when we simplify, then we can have cos of 360 degrees minus 60 degrees multiplied by tan of 180 degrees minus 30 degrees. And this we divide by sine of 180 degrees plus 45, and this is multiplied by cos of negative 45. Now I didn't change the 45 degrees, negative 45 degrees, because it's a negative angle, and negative angles start off, if it's less than negative 90 degrees, then it's in the fourth quadrant. So it being in the fourth quadrant, we know it will make cos positive anyway. So then, is it still clear up to so far? Up to this point, is everything clear?
Yeah.
All right. So the next step that we go through, when we reduce cos of 360 minus 60, that is fourth quadrant. Cos is positive, so we just have cos of 60 degrees. 180 degrees minus 30 degrees, its second quadrant, tan is not positive, so we'll have negative tan of 30 degrees. And then in the denominator, we will have negative sine of 45 degrees. And this will simply be cos of 45 degrees because it's a negative angle. Now, to further simplify, we can refer to our special triangles. And in our special triangles, we will have cos of 60. So for the 60-degree angle triangle, the cos of 60 will be adjacent over hypotenuse, which is 1 divided by 2. So we'll have 1 divided by 2 multiplied by tan of 30 degrees is opposite over adjacent. So it's 1 over the square root of 3. Then in the denominator, sine of 45, or rather negative sine of 45, is negative 1 over root 2. And the cos of 45 is also 1 over square root of 2. But in this case, it's positive. Then what we end up having is 1 divided by 2 the square root of 2 divided by a half. No, not square root of 2, square root of 3. My mistake. And I wrote this divide sign deliberately so that when we perform the operation of dividing a fraction by another fraction, we can see that the denominator becomes the inverse and then it's multiplied with the numerator. And we are just left with 1 over the square root of 3 because, let me write it a little bit further so it doesn't look like it's part of the solution. This is because 1 divided by square root 2 the square root of 3 divided by 1 over 2 equals 1 over 2 root 3 times 2 over 1. These two are multiplicative inverses, so we're just left with 1 over square root of 3. And that is the answer. So these problems, I'm being deliberate in sharing that we first come across them in grade 11, not to make you feel like we've forgotten some important things, but just to say, hey, we ought to remember that we learn everything and we keep adding stuff onto it as we go in our grades. So even when you get to first year and you do something with math, you will still be expected to understand the stuff you learned in the previous year, which is matric. Even if you last did matric 10 years ago or 18 years ago, like some of us. Ne? So yeah, another way these problems manifest. This cat above the roof. Another way these problems manifest is if you have, in grade 12, the angles start getting a little funny. And they get a little funny so that you think a bit more because they want to test that you're ready to leave school. So you only leave school if you can show that you can think beyond what it is that you've been taught before. So in our grade 12, Siyavula Learning Guide, on page 141, we've got the cos of 420 degrees minus the sine of 225 degrees multiplied by cos of negative 45 degrees. and this is divided by the tan of 315 degrees. Right? So, and this is actually a revision problem. In the textbook, it's literally written revision. So that's just to illustrate the point that I'm putting across. But the principle is the same. You solve it the same in grade 11 as you do in grade 12 and in your exam. But typically, these are like what? 5, 6, 7, maybe 8 marks, depending on, the examiner or the paper that you're writing. Right, so again, let's think of the angle 420 degrees as a compound angle. So 420 degrees, we can say it's 360 degrees plus 60, which makes sense because 420 degrees is more than 360. So we should add something to get to 420. 225 degrees. Let's see. If we take 180 degrees and we add 45, how much do we get? We should get 225, yes? And if we take 315 degrees, maybe if we subtract 45 from 60, that should give us, let's see, what's 60 minus 45? It should be 15. So 360 minus 45 should be 315. Yeah. So far, is it clear? Ooh, I think I should do this. Yeah. Who's just joined us? Is it Nobutle? Hi, Nobutle.
Yes.
Welcome.
Hello, good evening, everyone. Yep.
All right. So, yes, we're just carrying on from the discussion that we last had, which was about these angles, these trig ratios that we simplify, and we simplify them. Let me do this. We simplify them using the compound angle. Is it compound angles? Yes, compound angles, so to speak. I would say compound angles because we're gonna get into that. So this problem is a grade 12 problem, but it's more a revision exercise. So we were simplifying the angles 45, 225, and 315 so that we can simplify the trig ratios and then get to an answer. So cos of 420 degrees would be the cos of 360 degrees plus 60 degrees minus the sine of 225 would be 180 degrees plus 45, and cos of negative 45, I'll just leave it as cos of negative 45 degrees for now until we have reduced all of the angles and transformed or changed rather all of the trig ratios. So tan of 315 becomes the tan of 360 minus 45 degrees. All right. Then when we reduce 360 degrees plus is first quadrant, cos is positive. So we have positive cos 60 degrees minus 180 plus 45 makes sine negative because 180 degrees plus is in the third quadrant and sine is negative. Now, what happens is, since it's negative, we write the negative sign there, and we still keep in mind that before we changed this expression, before we manipulated this expression based on this angle and the quadrant in which it's positive or negative, the sign of the expression itself was negative. So we keep the negative along the steps. And then as we transform that, we put another negative there because this quadrant tells us that This angle tells us that in this quadrant, the trig ratio is negative. So we will have negative sine 45 and cos 45, because the negative 45 is less than negative 90, it puts us in the fourth quadrant where cos is positive. So this just remains cos of 45 degrees. 360 degrees minus is fourth quadrant and tan is negative there. So this becomes negative tan 45 degrees. Then in the next step, we'll just change the operation sign here so that it's positive. So we have the cos of 60 degrees plus the sine of 45 degrees multiplied by the cos of 45 degrees. And this is divided by negative tan 45 degrees. All right. We can use special triangles here. The first one we can go to is the 45, 45, 91, where the sides close to the 90-degree angle are 1 and the hypotenuse has a measure of square root of 2. And the other special triangle is 60 degrees, 30 degrees, and 90 degrees, and that's 1, 2, square root of 3. If you use mnemonics or sounds in your head that you can say in your mouth to remember the triangles, I usually go for this triangle. I start with the angle at 60 degrees and then I count my sides going counterclockwise. So it's 1, 2, square root of 3. And then I know the angle that remains is 30 degrees. And then for the 45-degree triangle, I know it's an isosceles triangle. So it will be 1, 1, and both of them combined give you square root of 2, so to speak. They don't really add up to 2, but 1 and 1 give you 2. But because it's a right angle triangle, and if you use Pythagoras, you will end up with square root of 2. So that's how I think about them, to remember them quick. So cos of 60 becomes adjacent over hypotenuse, and that's 1 over 2, plus sine of 45 is 1 over square root of 2, and cos of 45 is also 1 over square root of 2. Now these two, they multiply each other. So we need to keep that in mind. Now in the denominator, we have the tangent of 45 degrees. Tan is opposite over adjacent. So it doesn't matter which of the two 45 degrees you take. You can take this one. The opposite would be this side. You can take that 45 degrees at the top and the opposite would be the side at the bottom. Nevertheless, the tan would be 1 divided by 1, and that's simply negative 1. And this gives us a half plus a half divided by negative 1. And this simply gives us negative 1 as an answer. So the nice thing about problems like these where we have to reduce or simplify, they tend to often come to an answer that is ridiculously simple. So simple is hard to believe. But that's the beauty and fun of it. So you practice them long enough, you'll start seeing a pattern that kind of takes you in that direction. Sorry about that. So far, is everything clear? Yes? Okay. So I'll just move to the next slide. Now I want us to revise again trig problems that I know can be challenging, but they usually require us to think in terms of trigonometric identities. And these ones require us to be expert manipulators of, trigonometric expressions. So the next one is these ones where we prove stuff, right? So the ones we've done so far since the beginning of this class are just simplify, reduce the angles, etc. These kinds are now prove. So where we prove the left hand side to be equal to the right hand side. And this one, it's also it's a revision problem. Also on, it's a grade 12 problem, or rather grade 12 learning guide in Siyavula. So this is for if you want to go through the learning guide and practice the same problem. The nice thing about it is that it's a step-by-step problem. You see the step-by-step, so you can follow how they solve the problem. And this is page 141. I'm just making the note of the textbook. So we must prove that sine squared alpha minus tan alpha minus cos alpha times tan alpha plus cos alpha equals cos squared alpha minus sine squared alpha over cos squared alpha. So right off the bat, it doesn't really look like these two could be the same thing. But we have to prove that. So we have to manipulate one side or the other. So in the learning guide, they give us the privilege of proving that the left-hand side equals the right-hand side. Now, I would like us to prove that the right-hand side equals the left-hand side. So we'll start by saying the right-hand side equals, and here, if there's anything that seems confusing or whatever, just just give me a shout and then I'll explain whatever step where we get stuck at. Some of these, we don't have to prove that the left-hand side equals the right-hand side. We can just simplify each side separately, and then we'll get to a point where both the left-hand side and the right-hand side equal each other. So we can try that. So we can look first at the right-hand side or the left-hand side. It doesn't really matter. We'll do both. It's fine. So for right-hand side, we have cos squared alpha minus sine squared alpha divided by cos squared alpha. And this equals we can write cos squared alpha as what's this? First things first, our identities are sine squared theta plus cos squared theta equals 1, and we also have tan theta equals sine theta over cos theta. So I'll just put that there as a note, side note. So if we make, looking at the bottom here, if we make cos squared the subject of the formula, we get 1 minus sine. So we can have cos squared alpha minus sine squared alpha over 1 minus sine squared alpha. Then we will have or maybe not. That actually complicates it. Yeah. That actually complicates it. So let's rather just split the fraction, which if we split it, we will have cos squared alpha over cos squared alpha minus minus sine squared alpha over cos squared alpha. This gives us 1 because this is it's 1 something divided by itself. And here we'll have tan is sine over cos, so we'll have tan squared alpha. I don't think we can simplify it any further, but maybe the left hand side we can simplify that, so we will have sine squared alpha minus, if we look at this expression here, it is a difference of two squares. And if we have an expression that looks like a minus b times a plus b, this equals a squared minus b squared. So here that means we will have tan squared alpha minus cos squared alpha. And then that gives us sine squared alpha minus tan squared alpha plus cos squared alpha. And again, we have a square identity, which is sine squared plus cos squared equals 1. So here we have sine squared plus cos squared. So we can equate that to 1. And then we're left with negative tan squared. So it becomes 1 minus tan squared. Now right here, it seems we've reached the end of the line because our left-hand side and our right-hand side are equal. Therefore, we have proven that our trigonometric expressions are the same. The most important thing that we must always note when dealing with proofs like this comes to the denominators. We mustn't divide anything by 0. Because if we do, on our calculators, if we try that, we get an undefined. And when we get an undefined, we can't solve the problem going further. So because of that, we need to give a restriction. So cos squared of alpha we need to look at where it equals 0. So where does cos squared of alpha equals 0? Cos alpha equals 0 where alpha equals 90 degrees or 270 degrees. That means wherever, if we make a general case for alpha, so our alpha, if it's 90 degrees plus a factor times 180 degrees, because if we add 180 degrees to 90, we get 270. That means we must limit our trigonometric expressions or trigonometric ratios rather, so that wherever we find the denominator, we shouldn't get a denominator of 0. And we will get a 0 if alpha is 90 and we add it with 180 degrees, regardless of how many times we multiply that 180 degrees by. So what that means is alpha must not equal, so again, cos squared alpha, alpha must not equal 90 degrees plus k times 180 degrees. That's what this means, yes. So our identity is undefined at alpha equals 90 degrees plus k times 180 degrees. So in other words, if we, on our Cartesian axis, where we have 90 degrees and 270 degrees, and regardless of how many times we go around the Cartesian axis, we must avoid having the answers that give us 90 degrees. So it shouldn't be 90, it shouldn't be 270, If we add 180, that gives us, I don't know, but you'll just do the math on your calculator. So however many times on the vertical axis, the y-axis, where cos will always equal 0, we shouldn't have alpha equal that. So we must always put up that restriction to show that we understand that if we have this denominator give us 0, then this whole expression doesn't make sense. Again, if we go to we can do another problem. This one is from Mind the Gap. It's activity 8. It's on page 207. Activity 8, page 207. So the next one is sine of x times tan of x plus cos of x equals 1 over cos x. Again, x must not equal 90 degrees plus k times 180 degrees. And we must prove that it's valid. So we must prove that the left-hand side equals the right-hand side. That being said, this is a 4-mark question. It's 4 marks. So yeah, if we take our left-hand side, that equals sine of x times tan of x plus cos of x. This equals sine of x times sine of x divided by cos of x plus cos of x. This gives us sine squared of x divided by cos of x plus cos of x. And now we're going to do some addition. So I want you to think of fractions in the sense that if we have 1 over 2 plus 2, this gives us, it's 2 times 2 plus 1, so it's 5 over 2. All right? In other words, if it's a over b plus b, it'll be over b, so b times b is b squared. So these two are the same thing, it's just one is using numbers and they also are the same thing like that. So what we end up having is sine, maybe let me not start with the sine, so it's cos times cos, which is cos squared, plus sine squared x divided by cos x, and then this gives us 1 over cos x, and this equals the right-hand side. Does that one make sense? Are we following?
Yeah.
Okay. Guys, I hope you all don't mind. Are you hearing sounds like above my roof? Cause like there's a cat, I think, keeps jumping from the tree to the roof. Or is it? Could be something else. I don't know. Another example, same learning guide. we've got the sine of x plus the tan of x multiplied by the sine of x divided by 1 plus cos x, and this equals sine x times tan x. Right, so this equals bum, 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 bum. Bum, bum. Bum, 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 bum. So this is one of those where we might have to do some manipulation on both sides. So let's do that. So on our right hand side, we have the sine of x times the tan of x, and this equals the sine of x times the sine of x divided by the cos of x, and this gives us sine squared x over cos x. Maybe we can't go further. So we will look at the left hand side, and here we have sine of x plus tan of x. This is one expression multiplied by the sine of x over 1 plus the cos of x. This equals, now we're gonna do some distribution, so we can multiply the sine with the tan and again the sine with the sine. So that gives us sine squared x plus sine x tan x divided by 1 plus cos of x. Okay. Then we can then say, am I doing it right? Maybe not. Then we can have sine square of x plus sine x times the sine of x over cos x over 1 plus cos of x. That means I'll have sine squared of x plus sine squared of x over cos of x, and this is divided by 1 plus cos x. This is kind of going there, but it's kind of not going there. So maybe I'll need to rethink it. And if I rethink it, oh, Gosiam, this cat is so noisy. Can you guys hear that cat? No? Yes? No?
No, the Kate is very faint.
Is it?
We can hear it, but it's not bothering
It's
us.
not bothering.
I speak for
Oh.
Tebogo and Musa.
Because it's literally above my roof, so I can hear it, and it's annoying.
Rapela.
It's just a cat. I prefer cats because they're meat eaters, so they chase away mice and lizards and snakes, you know. But Uguti during class now it's on the roof. Hey, it's annoying, man. But yeah. So let's see. Maybe I shouldn't go about it this way. I'm gonna erase all of this and then start it again. I'm gonna erase everything and then start it again, so that I have a better flow. Alright, so I'm gonna convert tan into the quotient identity this time around. so that I try something different. So this is plus sine x over cos x, and this is times sine x over 1 plus cos x. Let's see, what do I get next? Okay, so then I can have sine x times cos x plus sine x, and all of this is over the cos of x multiplied by sine x over 1 plus cos x. Okay, then if I take out sine as a common factor here at the top, I will get sine x into cos of x plus 1 divided by cos of x, and I still have to multiply with sine x over 1 plus cos x. Then, this is interesting. So that means I can divide the 1 plus cos x with the 1 plus cos x. And this is going to give me sine squared x over cos x, yeah, over cos x. And at this juncture, the left hand side equals the right hand side, but again, x must not equal 90 degrees plus k times 180 degrees, because if that happens, then my denominator is, oh no, maybe that's not the case here, because even if cos x is 0, I still have a positive denominator, so I don't need to worry about the limitations on the denominator on this one. So again, it's still the same type of problem, like the same theme with these types of problems where we use identities to solve or to prove or to simplify. Now, there are compound angles that come from the fact that, remember when we have those quadrants where we define it's 360 degrees plus theta, 360 degrees minus theta, 180 degrees plus theta, and 180 degrees minus theta. And I guess we can also have 90 degrees plus theta, 90 degrees minus theta for co-functions, right? So from this, which are numeric, hold up, okay. Okay, so then I can fart. Gotcha. Oh, sorry. Yeah. I was just jamming some
Okay,
shui.
Catman.
Yeah? What?
I said, okay, Catman.
I was just jamming shui whilst you guys were taking time to log in.
Yeah. Year.
Yes. So yeah. So the next thing that we're gonna look at. So remember we have these angles. I get 180 degree minus, 180 degree plus, 360 minus, and 360 plus, and also some of the co-function ones. So from these, there are important identities that add on to our square identity and quotient identity. So square identity, again, just a reminder, it's sine squared plus cos squared equals 1. And quotient is simply tan equals sine over cos. Now, these angles here, they give us something called compound identities. Now, why they called compound identities is because, or compound angle identities rather. Let me write compound angle identities. Compound angle. Okay, so this is where maths becomes a little bit more abstract than we've been working with. And it's for us to really do some mental gymnastics. I know, Nobuhle, you and I like to laugh about how maths gets so abstract. It's too much mental gymnastics, ne? So I want the next 20 minutes to be a nice intro into compound angle identities. And that's because we've put quite a bit of emphasis on reducing angles like with 360 plus, 360 minus, 180 plus, 180 minus, ne? So compound identities include things like the sine of alpha minus beta, the sine of alpha plus beta, the cos of alpha minus beta, and the cos of alpha plus beta, right? In the next class tomorrow, we are going to derive these. But for now, I just want us to look at some of them, ne? And I want us to also note that the fact that they are compound lies squarely on the fact that the angle is the sum of two different sizes of angles. So it would be easier if they were numeric, but because now we are going into the part of math where these things become, we try to solve them for a broader range of angles. That's the whole point, right? So we will use one angle as alpha and represent it as alpha rather, and represent another angle as beta. and we'll say the difference of those angles or the sum of those angles is what we're going to look at. And each one is going to have its own expression, right? So the first compound angle identity is cos of alpha minus beta. And this is simply cos alpha cos beta plus sine alpha sine beta. It helps to commit this to memory, and I'll show you how. But that's the first one. The second one is cos alpha plus beta, and it equals the cos of alpha times the cos of beta minus the sine of alpha times the sine of beta, right? The third one is the sine of alpha minus beta, and it equals the sine of alpha times the cos of beta minus the cos of alpha times the sine of beta. And the last one of the compound angles is the sine of alpha plus beta rather equals the sine of alpha times the cos of beta plus cos alpha sine beta. Now, in order for us to commit them to memory, I want us to note the following. I'm going to use the blue color to note some important things on the first compound angle identity. And I want to pull your attention to the operation signs in the expression. So the minute you see cos alpha minus beta, what must come to mind? Sorry, is there something?
No, Debocho's mic is not muted.
Oh, okay. It's Tiamo. Yeah, Tiamo's using mom's phone. Let me mute so that it doesn't disturb us. Yeah. All right. So here, the sign is negative, but you convert it to positive that side, and you start off with cos of alpha, and then you go cos of beta, and then you do the same for sine post this operation sign. That's the first compound angle identity. Now with the second one, you do the opposite. If it's plus there, then between the products of the trig ratio sine, and cos, it's negative. And then you start with the alpha and then you go with the beta. With the third one, for sine alpha minus beta, instead of sine alpha followed by sine beta, it's sine alpha followed by cos beta. So the signs are the same, but this time alpha goes with sine and beta goes with cos. And then post the sine, the alpha goes with the cos and the beta goes with the sine. And in the fourth one, the sine, the operation sign between the product of the two trig ratios is the same as between the compound angles, but between the first pair of trig ratios is sine alpha and then cos beta, and then the alpha again goes with the cos in the second pair of trig ratios, and again the beta goes with the sine in the second pair. So it's gonna look a bit messy right now because we're just starting them, especially for you, Nobuhle. But for now, just bear with us, ne? The reason is because it usually helps to be able to identify them. I just want to check with some exam formula sheets if they give us formulae for these ones, because what I did when I was writing the same paper, I would commit them to memory. So I just want to check. They give you the formula, ne?
Yeah.
Okay. I'm actually glad they do, because they can be quite a handful to try and memorize. But the fact that they give them in the exam makes it so much simpler. It makes everything so much simpler. So, nevertheless, yeah, they are the first they are the first king, I guess, where the angles are a bit more sophisticated. The first type of identities where the angles are sophisticated. So these are the first group of angles that are sophisticated. The next one that we're going to come across is double angles. And double angles look something like this. I almost wrote double angels. Hey, the spelling can be very slight between angle and angel. So just be careful of that. So then we have double angles. So the first one is sine of 2 alpha, which equals 2 times sine alpha times cos alpha. And the second one is cos of 2 alpha, and that equals cos squared alpha minus sine squared alpha. And this can also be written as, if we use the square identity, then sine squared is 1 minus cos squared, and cos squared is 1 minus sine squared. Then if we substitute this in there, we get 1 minus 2 sine squared alpha, and if we substitute sine there, we get 2 cos squared alpha minus 1. And what this just means here is that all these three can be used interchangeably to express this double angle. But here, this double angle can be expressed like that. So a double angle simply means that if you have your angle like that and it's theta, then you have the same type of angle, then the sine of that, or the cos of that, is expressed like this. And in here, we simply have alpha there and beta there. And we're looking at the trig ratio of the two. Now, one thing we should also note is that we don't have an expression for tan. Neither do we have that for alpha plus beta for tan. It doesn't look like we have them. I wonder why, but we could probably ask around and find out. I really don't know. But I would like us to pause here and then continue with the proofs of these compound angles. So the proofs are necessary because the same way we do some of the mental gymnastics when we are solving these problems, it always helps to think about how these things come about. And because we contemplate how they come about, it sort of helps us better understand how we can solve these things. But yeah, before we close tonight's class, do we have questions? Are there any questions?
None from my side, thank you, Tutor.
All right. Musa? Sharp. And then Tiamo? You can unmute now.
I'm alright.
You're all right. All right. Yeah, you mustn't skip my classes, ne? Let's hear.
Tutor?
Yeah?
Oh, sorry.
I'm still here.
Sorry. May you please excuse me for tomorrow's class?
Oh, okay. All right. It's fine. We'll have class. It's okay. But we'll see you on Monday, Mus.
Yeah.
All right.
Alright.
Okay, but I wouldn't. Okay, I understand you'll have to be away for one reason or another. It's just not too many Saturdays, no.
It's out of my control.
Oh, is it one of those work-related things?
Yeah.
Is it okay? But we'll talk. It's fine.
Alright.
Alrighty. Have a good weekend, and yeah, you be superwoman there at the work there. I know they
Thank you. That must enjoy your weekend too.
sharp. Thanks, we will.
Thank you.
Alright, sharp.